Hello, in this video we're going to talk about Cauchy's functional equation, which is one of the most important functional equations that come up in math competitions quite frequently. So here's what it says. It states, it says that let f from R to R be a function satisfying f of x plus y equals f of x plus f of y for all real numbers x and y. Then f of R equals R f of 1 and for every R in Q. Furthermore, if f satisfies one of the following, either f is monotone or f is continuous at 0, then there is a constant c for which f of x is equal to cx for every x in R. If you don't know what a continuous function is, don't worry about that. Just you can follow everything except for the last step about continuity of f at 0. So let's just start with the idea of the solution to this problem. So the way I solve functional equations is always start with plugging different values for this, for x and y in this case. So I start from, okay, can I evaluate f of 1? Can I evaluate f of 2? Can I evaluate f of 3? So looking at what they gave us, everything is supposed to be given in terms of f of 1, which means I shouldn't really be able to evaluate f of 1. But let's see if I can evaluate f of 2. So if I look at f of 2, that would give me f of 1 plus f of 1 by substituting x and y by 1, which is 2f of 1, which is exactly what I wanted. And if I do f of 3, that would be f of 2 plus f of 1, which is 2f of 1 plus f of 1, which is 3f of 1. And if I substitute by 4, x and y by 3 and 1, I get f of 3 plus f of 1, and that's exactly what I wanted. So we can do this thing over and over, and we'll get f of n equals n f of 1 for n positive. Now, how about when n is and n is an integer? How about when n is negative or 0? For 0, we could look at f of 0 as f of 0 plus f of 0, because 0 is 0 plus 0, and that means f of 0 must be 0. So we can also show that f of 0 is 0 times f of 1. Now, how about f of negative 1? So if you think about negative 1, we can use 0 and 1 to get f of negative 1, because f of 0 is f of negative 1 plus f of 1, since negative 1 and 1 add up to 0. Now, this side is 0, so that means f of negative 1 is negative f of 1. How about f of negative 2? Well, we can do the same thing again. So f of negative 2 plus f of 2 would be f of 0, and then from here you can get f of negative 2. Negative f of 2. In fact, if you have f of positive numbers, you can get f of all negative numbers. In other words, f of x plus f of negative x is going to be f of 0, which is 0. So f of negative x is going to be negative f of x. So this means I can get f of all integers are n times f of 1. Okay, so this is true for every integer n. Now, how about rationals? Because I'm not quite done yet, so I have to show that for rationals. How do we show that for rationals? Let's just start with another example again. So let's say you want to find f of 1/2. So how do I find f of 1/2 using f of rationals? Well, I know that I can add 1/2 to itself to get an integer. So f of 1/2 plus f of 1/2 is f of 1, which means 2f of 1/2 is f of 1. So that means f of 1/2 is 1/2 f of 1. So that's good. How about if I want to find f of, let's say, 4/5? How would I evaluate that? Well, you can do this same kind of thing. F of 4/5 plus 4/5 5 times plus 4/5 plus 4/5 plus 4/5. So that's 5 times f of 4/5. because of the property that they gave us. F of x plus y is equal to f of x plus f of y. But the left side is f of 4. And that's exactly 4f of 1. So 4f of 1 is going to be 5f of 4 fifths, which means f of 4 fifths is going to be 4 fifths f of 1. Okay, so it looks like we can imitate this for any rational number. Now, going back and looking at the other two parts of the problem, we want to use monotonicity and also on the other side, the other case, continuity of f to show that in fact f of x is always c times x. For numbers that are not rational, for irrational numbers, we will have to use approximation of rationals using approximations of real numbers using rationals. And that gives us f of x for every x. So let's get to the solution now. So it looks like we now have a solution for the problem. Okay, but we're going to organize this in a fashion that makes sense. So how do we do f of n equals n f of 1? Well, we kind of see that the way we did it was by inductive ideas, because we found f of 4 in terms of f of 3, and then f of 3 based on f of 2, and f of 2 based on f of 1. So we can use induction here. So by induction on n, we will prove, and if you go back and look at what we did f of n equals n f of 1, but here we also use the fact that f of 5 times 4 fifths is 5 times f of 4 fifths. So why don't we prove that one for every integer and for every real number x? So in other words, by induction on n, we will prove f of x, f of nx is equal to n f of x for every real number x and integer n greater than or equal to 0. Okay, so we'll prove that one. So basis step would be for n equals 0. So for basis step, f of 0 is equal to f of 0 plus f of 0, which means f of 0 is 0, which tells us f of 0x is 0f of x. Okay, so that proves the basis step. Inductive step. Assume that this is true. Assume f of nx is n f of x for all x in R and some integer n. Then f of n plus 1 x is going to be f of nx plus f of x by the additivity that we had before, f of x plus y equals f of x plus f of y. And this is n f of x by inductive hypothesis plus f of x, which is n plus 1 f of x. So this completes the proof of the claim. Now we're going to look at negative numbers. Now note that f of negative x plus x is equal to f of negative x plus f of x. Okay, f of 0 is 0, so this is 0 equals f of negative x plus f of x. And if we bring f of x to the other side, we get negative f of x is equal to f of negative x. And that proves what we wanted to show. Now, therefore, f of nx is equal to n f of x for every real x and every integer n. So this only proves it for integers. I prove only f of n is equal to n f of 1. Now, how about rationals? So let R equals A over B be a rational number with A and B integers. The way we handled this was we added a bunch of copies of A over B to get to an integer. So f of B times A over B is equal to B f of A over B. Let's call this one star by star. F of B times A over B is equal to f of A, which is A f of 1. This is also by star. Therefore, these two are the same. Therefore, B f of A over B is equal to A f of 1, which means f of A over B is equal to A over B f of 1. Replacing A over B by R, we get f of R equals R f of 1 for every rational R. So this completes the proof of the Cauchy functional equation, the first part. Now, let's assume that f is monotone, and we are going to prove that f is in fact x times f of 1. So we wanted to prove this. Now we are looking at the furthermore part. Okay, so let's assume f is monotone. Let's just take the case when f is increasing. So suppose f is increasing, and let x be a real number. So the way we want to prove this one is by using the fact that you can approximate all real numbers by rationals. And this is a well-known fact. So let Rn and Sn be sequences of rationals such that Rn is less than x Sn. So I want to squeeze x in between rational numbers with Rn approaching x and Sn also approaching x as n goes to infinity. So I'm squeezing x between two rationals. Now, since f is increasing, I can take f from all sides of this inequality, and that gives me f of Rn is less than or equal to f of x less than or equal to f of Sn. Since Rn is rational, f of Rn is Rn f of 1, and f of Sn is Sn f of 1. If we take the limit, we get the limit of Rn f of 1 as n approaches infinity is less than or equal to f of x less than or equal to the limit of Sn f of 1 as n approaches infinity. However, if n approaches infinity, Rn approaches x, so the left side becomes x f of 1 less than or equal to f of x, and the right side is also x f of 1 because Sn also approaches x, and that's exactly what we wanted. So f of x becomes x f of 1, and the proof when f is decreasing is nearly identical. So the proof for when f is decreasing is similar. Now assume that f is continuous. So now assume f is continuous at 0. Again, we want to show f of x is equal to x f of 1. So let x be in R and Rn be a sequence of rationals that converge to x. Okay, so since Rn converges to x, x minus Rn converges to 0. So limit of x minus Rn is 0 as n approaches infinity. Now we know that f is continuous since f is continuous at 0. Limit of f of x minus Rn is going to be f of 0. F of 0 is 0. So that means limit of, we're going to use the property of f. It is f of x plus f of negative Rn. F of negative Rn is negative Rn f of 1. So this is the limit f of x plus negative Rn f of 1, because Rn is rational, and that's 0. If we take the limit of f of x is just x, because that doesn't depend on n. Limit of Rn is x because we chose Rn in a way that it converges to x, and of course f of 1 is a constant, and that means f of x is x f of 1, which completes the proof of the Cauchy functional equation. If you like this video, make sure to subscribe to the channel. You'll be able to find more videos like this on my channel. You should also see videos on functional equations that appear on the screen. Click on those videos and I will see you in the next video.